Good evening, all of you. Is my voice clear to all? And the video also? Right. So, in the previous sessions, we have discussed the concepts of cyclic groups and some basic definitions. So, in today's session, we want to discuss some more results on the cyclic groups results. And as well as the problems related to that we go on to discuss in today's session, right? So you please take a note of that. Then we start our today's session. So the first one is every cyclic group is abelian. So it is our first result. So let us think how to prove this result. So you consider G is a cyclic group, whether it is finite or infinite, and you take that G is generated by the element A. Now, to prove that G is abelian, we have to show that if we take any two elements in G, they will satisfy the commutative property that we have to show. So you take the two elements, X and Y belongs to G. Since it is generated by A, it means that every element in G can be represented in powers of A. So we can write that X equal to some A power M and Y equal to A power N, where the values belong to Z. Because it is generated by the element A, so whatever the value you consider in G, that we can mention in the power of A. So if you consider the product xy, it is nothing but A power M into A power N equal to A power M plus N. Since the values in the power are nothing but integers, this you can write it as A power N plus M equals A power N into A power M equal to Y into X. So from this point, you can say that it is an abelian group. So any questions you can ask? After noting, please tell. Right. Now, there is a small question arises that if you take an abelian group, will it be cyclic? So if you think about the converse of the result, so if you take an abelian group, will it be cyclic always is a question. Now the answer is clearly no. So for this, we can take a counter example. There are many examples, out of which I just want to take a small example that you consider the 2 by 2 matrices. Say you say A is equal to the identity matrix 1 0 0 1. You can take B is equal to C is equal to minus 1 0 minus 1, and you can take D is equal to, let's say this is 1. So you take the 4 matrices like this, A, B, C, D. Now, if you construct a composition table, under the matrix multiplication, you can observe that it is abelian. Say, since this is identity matrix, you can have the same thing. So first row, first column will coincide because A is the identity matrix. So if you do the remaining part, you will get the values as so you can observe that each row, each column, both will coincide. So row entries is equal to the column entries. So from this, you can say that it is an abelian group, and it is finite also. Are you clear over this, what I am saying? Yes or no? You can check on that, whether these entries are coming or not in this pattern. Now the question is, it is not a cyclic group. Why? Because among these matrices, you can consider any matrix that if you keep on raising the powers, you will not get the remaining matrices. Accepted? So among these 4 matrices, you can consider a matrix that if you keep on multiplying the matrix, you will not get the different matrices in this group. So it is not cyclic, but it is abelian group. So this is one good example that every abelian group need not be cyclic always. Okay? Clear to all? So please take a note of it. Shall I continue? Say. You are talking this one. So if you consider the values, so can you get the remaining matrices here? Can you get the remaining matrices here? So it is not at all a generator, right? It is not at all a generator. So if you want to say cyclic means in these 4 matrices, you can find one matrix such that if you keep on raising the powers, you should get the remaining 3 matrices. So will it happen in the 4 matrices what you have taken here? So that's why it is just a finite abelian group and it is not cyclic. Okay. So any other queries from anybody on this context? Fine. So can I erase this? Right. So there is one more concept that if you take order of G is equal to a prime number, then G becomes cyclic. This is also a good result. In other words, if you generalize the statement, a group of prime order is cyclic. So this is another good result. You take a note of this. A group of prime order is cyclic. So here the result is very simple. You take that order of G is equal to P, a prime number. Now the question is, since you have taken that the number of elements in the group a prime number, so what is the possibility that the minimum number of elements in G should be what? Can you say? What would be the minimum number of elements in G? Because prime numbers starts from 2 onwards, you can say that order of G is greater than or equal to 2. It means that whenever you take a group G, it obviously contains the identity element and other elements also. Do you accept? So, in this context, we can say that, let us take that the other element is A. If you take that G is a group, then it obviously contains identity element and it contains other elements also, say A, because order of G is greater than or equal to 2. So in the beginning of cyclic groups, we discussed that always the set is a cyclic group. Because as and when you take an element, always it will possess the order. Because you are saying that the group has prime order, so obviously G is a finite group. So if you take any element in G, it is also has a finite order. So definitely, if you take that order of A is equal to n, then the set of values you can say a power 1, a square, so on, a power n. This is nothing but a cyclic group. We accept it or not? Yes or no? So for every element A belongs to G, you can consider the powers of A, that is always a cyclic subgroup of G. Accepted? So you have taken a part of it. So this is the part of G, so which is nothing but it is generated by A. Since it is a subgroup of G, you can say that order of H divides order of G. We accept it. So at this point, you can say that order of H divides the prime number. Since P is a prime number, the possibility for H is nothing but either order of H equal to 1 or order of H equal to P. So these are the only two possibilities for H. So if you consider the first case, it is not possible. Why? Because H is generated by A and these two are distinct elements. Since E is not equal to A, so order of E is not equal to order of A, which is nothing but order of H. So 1 is not equal to order of A, nothing but order of H. So this case is not possible. Hence, the only possibility is order of H is nothing but P. So you are saying that the subgroup H and the group G both have equal order. Therefore, immediately you can say that H is equal to G. Since this is cyclic group, G is also cyclic. Hence, the proof is complete. Clear how we have proved? Are you clear with the logic? So here you have taken that a group of prime order. That's why I have taken P, where P is a prime number. Okay. So we are saying the fact that order of G a prime number. So if you say that order of G is equal to n, then n is prime. This is our hypothesis. So based on this hypothesis, you are proving that it is cyclic. Okay. Are you clear? Everyone. Right. So let us take one interesting thing that every subgroup of cyclic group is cyclic. You take a note of this. Please take a note of this. So is the question part clear? Every subgroup of a cyclic group is cyclic. Now let us say the approach of the problem. So in the first step, you take that G is a cyclic group generated by A. Now you take that H is any subgroup of G. Now, as per the question tag considered, we have to prove that H is cyclic. This is our claim. So it is nothing but you should be able to show that H is generated by some number. So what is the number? You need to identify that, hence the claim will complete. Okay? The approach of the problem? Yes or no? Now the thing is, since G is generated by A, it means that whatever the element you take in G, it is nothing but a power of A. So it is just like A power 1, A power minus 1, A power 2, A power minus 2, so on. So G is totally filled in powers of A. Since you are taking a part out of it, H also contains powers of A. Accepted? Because H is a part taken out from G. So, since H contains the powers of A, among the powers, you can choose the smallest power. So, let us take that A power D is the smallest power element in H. This is our consideration. Now, to prove that H is cyclic, I want to show that this is generated by the A power D. This is my claim. So I want to show that this smallest power element in H will generate the whole set H. So that H becomes cyclic, hence the context of the problem is proved. Accepted? Say. Now the question is, how can we show that this element generates the whole set H? Can you tell? What is the pattern we need to follow to show that this element A power D will generate the whole set H? Any logic, any idea? So here, my intention is, in H, if you take any element X, then you can write X is equal to A power D power something. So if you have shown this, so whatever the X you take in H, that we are able to represent as power of A power D. Therefore, H is generated by the element A power D. Accepted? So, is the ideology clear? We are going to show that every X can be written as A power D power something. Hence, H is generated by A power D so that it becomes the context. What you are going to prove. Is that fine? Right? Now let us start with the approach. Now you take that x belongs to H. Since H is a part of G, this x also belongs to G. So this x can be written as power of A because everything is taken from the group G. So you can write x is equal to A power m, where m belongs to Z. Now the question comes that in the set H, you have taken the value A power D, which is already there, and you have taken other element A power m. So you have basically m and d are integers. Accepted for all the things what you have taken. Now, whenever you take integers, you can apply division algorithm. Hence, you can write that accepted this result, division algorithm. Whenever you take two numbers, you can write dividend is equal to divised into quotient plus remainder. We have solved similar kind of problems at the school level. What is meant by division algorithm? So we have x belongs to H and x equal to A power m. Therefore, you can say that so this thing you have written like this. Now the question is, R 0 or R is greater than 0. Now, after applying division algorithm like this, if you consider x, the value of x will become like this. Now the question is, while considering the powers, is R 0 or not 0? Now what happens if R is 0? Then from this expression, you can say that x is equal to A power D whole power Q. Therefore, H is generated by A power D. You accept it or not? Because x is any arbitrary element in H and you have represented x as power of A power D. Therefore, the whole subgroup H is generated by A power D. Accepted to everyone? Right. Now, I am going to prove that if R is greater than 0, you will get a contradiction. So, the only choice for R is R must be equal to 0. Hence, this type of phenomena will appear. Okay. Now, let us check what happens if R greater than 0. So, what happens if R greater than 0? So, you have so this is nothing but this implies A power m minus dq is equal to A power r. This is the thing you have. Now, from this pattern, you can say that A power m belongs to H, A power d belongs to H. So, A power dq belongs to H, A power minus dq belongs to H, a power m minus dq belongs to H because it is a group. Accepted from the picture? Are you getting this or not? I will draw a big picture for your idea. So you have taken H here. You took a power d. So you can say that a power dq belongs to H because closure law. So a power minus dq belongs to H. This is inverse law. Already you have taken a power m belongs to H. Therefore, a power m minus dq belongs to H again by closure law. Accepted? All of you? Please tell. So, this is nothing but a power r belongs to H. So, but you have taken that 0 less than or equal to r less than d. So, if r is not equal to 0, then you have 0 less than r less than d is the thing. So, you are saying that a power r belongs to H. So, actually, this is a contradiction. Why this is a contradiction? Because initially you have taken that a power d is the smallest power element in H. So if you take this case 0 less than r less than d, so you are saying that a power r, a power d. So this is happening to be that a power r belongs to H. So this is absurd. Clear? Why a power r should not be in H? So that's why you have two cases, r equal to 0 and r greater than 0. So if r is greater than 0, you will get a contradiction. Hence the possibility is r equal to 0. So you can say x is represented as power of a power d. Hence h is generated by a power d. It becomes cyclic. That is the solution of the problem. Any questions you can ask? Please tell. Are you clear, all of you? Then I take the next result. If you have noted this, after noting, please reply. So I'll take the next problem. Now, if G is cyclic, then the quotient group G by N is cyclic. It is an interesting phenomena. So whenever you take a cyclic group, so for every group, it is possible to find a normal subgroup. Immediately, as and when you have a normal subgroup, you can calculate the quotient group. So the structure here is, if this is cyclic, then this is also a cyclic. So from this very observation, you can say that if this is the set G, containing only elements, and this is the set G by N. It contains cosets. So G by N is cyclic, means whatever the coset you take here, so every coset is generated by a basic coset. Are you clear? So there exists a basic coset which generates all the remaining cosets. So if G is cyclic, corresponding G by N is also cyclic. You take a note of it and we discuss how to prove. Are you clear with the context? Right. Now, let us take that G is a cyclic group generated by the element A. It means that every element in J is a multiple of A. Now what happens? For every element in G, corresponding coset will be here. So if I take X, the corresponding coset is Nx. If I take Y here, the corresponding coset is Ny. Now let us prove that there exists a basic coset which generates all the cosets in G by N. It is very easy. So let us take that Nx belongs to G by N. So this implies you can say X belongs to G. So from this you can say X is equal to A power N, where N belongs to Z. That you take a note of it. Now for this Nx, you apply both sides N. So this is nothing but so applying the coset multiplication, as you know, HA dot HB is equal to HAB, the property of coset multiplication. Applying the same thing here, it is nothing but NA dot, so on NA, N times. So nothing but NA whole power N. You can observe that this coset Nx is represented as a coset whole power N. So this is generating this thing. So G by N is nothing but generated by NA. So if you take that G is generated by A, the corresponding generator is nothing but NA. Are you clear what I am saying? So please take a note of it, then we discuss the other contexts. After noting, please tell. Shall I continue? Right. Now, this is another interesting result. You just take a note of it and understand the content. So whatever the infinite cyclic group you take, it always contains exactly two generators and they are nothing but inverses to each other. So if you say one generator is A, the other generator is nothing but A inverse. So these are the only generators available for an infinite cyclic group. That is the context of the problem. Clear? So after noting, please tell, then we discuss about the procedure. How we are going to prove it. Right? Now, the thing is, let us say that G is generated by A and G is infinite cyclic group. So fundamentally, we discussed that whenever you have a cyclic group and a generator, the common phenomena between them is nothing but order of the group is equal to order of the generator. Accept it? Because for a cyclic group, order of the group equal to order of the generator. So this is a very interesting point we need to know. So from this, you can say that this is infinite. Because you have taken that G is infinite, so order of A must be also infinite. That we have to keep in mind. Now, as we know, G is nothing but the values generated by A. So, since we are talking about generators, let us take any other generator of G. So let us take that A power m is any other generator of G. So what does it mean? You are saying that G is generated by A power m and initially you are taking that G is generated by A. So it means that here G contains the values A and the powers of A. So there you are saying that G contains A power m and powers of A power m. Accepted? As per our discussion taken. So every element here can be written as a power of this and every element here can be written as a power of this. It is possible because for G we have two expressions. Yes or no? You accept for it? Now, I am saying that you can write A as the power of A power m. It is possible because for G you have two representations. You can write A as a power of A power m, and you can write A power m as a power of A here. Now, from this point, you can say that A power mp minus 1 is nothing but accepted, multiplying both sides with A inverse. Now, what about this power mp minus 1? Is it equal to 0 or greater than 0? This is a question. Now, what happens if you say this is greater than 0? So, you got that A power some number is equal to identity. Do you accept this? If you say this value is greater than 0, say yes or no? So, whenever you say that while raising the powers of A at a particular number, you are getting identity, it means that order of A is finite. But as you know, order of G is equal to order of A, and order of A is infinite. This is not correct. So you cannot say that mp minus 1 is a positive value other than 0. So the only possibility is mp minus 1 equal to 0. So this must be compulsory. mp minus 1 must be equal to 0 is compulsory. Now if you say that basically p is an integer, m is an integer. So if you talk of integers, I am saying that I have taken two integers, the product is 1. Because when you say that mp minus 1 equal to 0, this implies that mp is equal to 1 and m and p are integers. Then if you say that the product of two integers is 1, what are the possibilities for them to get 1 as the product? You cannot say the inverse because they are integers. If you take real numbers or rational numbers, if you say one number is 2, the other number is 1 by 2, it has inverse. But in integers, you cannot have inverses to numbers, right? You cannot take the reciprocal because they are integers. Please understand. Both the numbers are integers. They will not contain fractions. Are you getting the context, all of you? So the only possibility for them is nothing but m and p both must be 1 or m and p both must be minus 1. Then only you will get mp is equal to 1. Accepted? Yes or no? So, as we have mentioned that A power m is any other generator of G. So, m has only two possibilities. So, m is equal to 1 or m is equal to minus 1. So, if you take m is equal to 1, A is the generator. If you take m is equal to minus 1, so A inverse is the generator. It is an integer. It is just an integer, because you can write a as a power of a power m. That number I am taking it as p. Okay. From this expression I have taken this. Right. So as per the choices of m you have taken, from this you are saying that any other generator of G is nothing but a power m. So substituting the possible values of m, the only generators are nothing but a and its inverse. So they are inverses to each other is satisfied here. Clear? That was the solution of the problem. So if you are interested, I just want to represent the whole summary in stepwise as a small diagram. Can I? This is also one of the previous year questions. It is very simple logic. We will say that. So in a simple nutshell, it is just like this is first step. Let us take that G is equal to a power m. From this you can say that as so from this you can say that so here we have bifurcated like this. If you take this thing, you will get a contradiction. So if you take this thing, you can say that m is equal to 1 or m is equal to minus 1. As so from this, substituting here, you will get that G is equal to A or G is equal to A inverse. That's all. This is the whole synopsis what we have discussed. So is it comfortable to understand the idea? So please take a note of it, then I go with the other concepts. After noting, please inform. You just take a note of it. This is also an interesting thing. Any infinite cyclic group is isomorphic to additive group of integers. After noting, please tell. Now, so here the thing we have to show that we need to construct an isomorphism between infinite cyclic group and the group of integers. That is the actual thought here. So here, if you say that G is generated by a power a and z comma plus you take, then our claim is G is isomorphic to z. That actually we have to show. So in other words, you need to construct a function from G to Z such that it is a 1-1 function, onto function and homomorphism. So obviously we are able to prove that these two will become isomorphic. Okay? The outline idea for it is. Now the question is how to construct an isomorphism between these two. That was the question. Clear? Now, as you have taken that G is infinite, so G is nothing but generated by A, means set of all a power n where n belongs to Z. So, and all these powers will give distinct elements in G. Because G is infinite. Accept it all? Now, we are going to define the function as you just define the function as f from G to Z by f of a power n equal to n. Now, by showing that this function is a bijection as well as homomorphism, the problem will get completed. Please take a note of it. So if you take two elements, then you can say that x is equal to a power m, y is equal to a power n. Therefore, if you consider f of xy, this is f of a power m into a power n. So a power m plus n very simple. Let me say this all contains red balls. This all contains blue balls. So how you go on to pair? One red is equal to one blue. Yes or no? Similarly, if you say that this is cyclic group, this is all nothing but powers. And here, powers are nothing but integers. Accepted? So, in the domain, whatever the element you take, in the codomain you just have integers, so you respect the map there. You map them in that manner. Clear? That's it. So this is homomorphism, and you can easily verify 1, 1 and on 2. There is no need to prove that separately. I think you can manage how to prove 1, 1 and on 2. If you have a doubt, then I will prove how to prove 1, 1 and on 2. Is it required for you? So please take a note of this. From this perspective, you can say that these two are isomorphic. Shall I continue then? Right? Now the question is, as you are taking that infinite cyclic group, now what about the finite cyclic group? So if you take the finite cyclic group, so it is isomorphic to additive group of integers modulo n. So it is nothing but, so g comma dot is isomorphic to zn comma plus n, where n is equal to order of g. Here also we prove the same content by defining the same function. So proof is no difference at all. The proof is very same, no change at all. The thing is, if you take the infinite cyclic group, it is isomorphic to z comma plus. If you take a finite group with n elements, it is isomorphic to zn, the integers modulo n. Just like if you take order of g is equal to 5, then it is isomorphic to z5 comma plus 5. So where z5 is nothing but 0, 1, 2, 3, 4. That is all about the finite case. Okay? So there is no need to prove the finite case separately, but you keep a note of it. So this result is applicable for as well as finite cyclic groups and infinite cyclic groups also. Okay? So can I take the other model? Right? Now, the interesting thing is, let us take that you take that G is a cyclic group generated by A and order of G is equal to N. So the question is, A power M is generator of G if and only if GCD of M comma N equal to 1. So this is also an interesting result. You take a note of it. After noting, please tell. Is the context clear? What we are actually proving there? All of you? Yes or no? Yeah, I will say. So G is a cyclic group, means here every element in G is power of A. Accepted? Now, for a cyclic group, there will be so many generators. Let me say, if G is generated by an element X, since initially every element in G is a power of A, this X is also a power of A. So you can say that X is equal to A power M. Agree? So whenever you say that A power M is a generator of G, then these two numbers must be relatively prime. That was the question. I will explain a thing, right? Let me say, you give a number to me. You give a number for order of G to me. Not a prime number, you give other number. 8. Now let us say G is generated by A. So that is order of A is equal to 8. Yes, right? Right. So from this perspective, we can say that A power 1 is generator, A power 2 not a generator, A power 3 generator, A power 4 not a generator, A power 5 generator, A power 6 not a generator, A power 7 is a generator, A power 8 is not a generator. Why? Because GCD of 3 comma 8 1, GCD of 5 comma 8 1, GCD of 7 comma 8 1. Are you getting the context here? What it is actually? So here, if you observe that GCD of 2 comma 8 2, GCD of 4 comma 8 4, GCD of 6 comma 8 2, GCD of 8 comma 8 8. So these are not generators. So if you know one generator, you are going to find all the other generators of G. And I will say that phi of n generators you will have generally. So what is phi of 8 here? If you observe, so it is nothing but 8 is equal to 2 cube. You apply the formula 1 minus 1 by 2. So 8 into 1 by 2. So you will have 4 generators. So the 4 generators are nothing but A power 1, A power 3, A power 5, A power 7. These are the 4 generators we will have. Because whenever you will get a cyclic group, it will contain phi of n generators, where n stands for order of the group. So if I say the group order is 8, it will have phi of 8 generators. Applying the formula, I will get 4 generators for it. So what are these four generators? If you say that A is a generator, the remaining generators are nothing but A cube, A power 5 and A power 7. Okay. Is the context clear for everyone? Any more doubts? So if you know one generator, you are able to calculate all the remaining generators for the group. That is the advantage of this result. Any more questions for anybody? Let us take one more example. So let us take that order of G is equal to 12. Say G is generated by A. So what are the remaining generators? So it is nothing but, if you consider the numbers, A power 1 is a generator, A power 5 is a generator, A power 7 is a generator, A power 11 is a generator. So total 4 generators. So if you consider phi of 12, as 12 is equal to 2 square into 3. So phi of 12 is equal to 12 into 1 minus 1 by 2 into 1 minus 1 by 3. So 4. This is the thing. Please check on that. Because if you observe the powers, A power 1, A power 5, 7, 11, they are relatively prime to 12. The powers what you have written, A power 1, A power 5, A power 7, A power 11, they are relatively prime to 12. That's why these are nothing but the generators of the group G. So if you want to satisfy that the total number of generators are achieved or not, you can check that for any cyclic group of order n, phi of n generators will be there. If you calculate phi of 12, its value is nothing but 4. It is satisfied there. Okay? Clear now the whole context? Any more queries for anybody? So at this context, I want to stop our today's discussion, and tomorrow we will meet with the new concepts over the cyclic groups and other concepts of group theory. There we can wind up our discussion on group theory, and we start with the new module, that is ring theory, which is the second part of abstract algebra. So as far as my opinion is concerned, there is no need to go for separate reading of any books, etc. If you keep these results in mind and you are able to solve the previous year questions, I have covered many of them in our class discussion so far considered with respect to group theory is taken. Okay. And due to some reasons, the last 2 classes gets cancelled. So it will be compensated in the next sessions also. So don't worry about that, whether the respected number of classes are taken or not. So there is no need to think about them. Clear? So if you want to add any other things, you can add. And I feel that if you take the abstract algebra classes at a stretch, then in the middle you will get boredom, because you are doing a lot of theory here apart from the regular problems. So as and when you get time, you can think what happened so far with regard to abstract algebra. So you can boost up the knowledge with regard to the previous concepts, and upcoming sessions will be interesting for you. That I can assure you. Okay. So thank you very much for everyone. And that's all for today. We will meet in the next class. If you want to say something, you can add. So we were going to take the concept of numerical methods. So can I say one thing? In the whole syllabus, what are the critical things which you have to encounter as per the syllabus part is considered? One is abstract algebra, which we will never read at your college level. Second, real analysis. Third, fluid dynamics, you agree? And mechanics, statics. These are the 5 things. However, you can come up with complex analysis up to some extent, and PD some extent not in depth of it. And vector calculus is also you are familiar with that. But consider to these 5 topics, it is very critical, say, because you are learning for the first time, isn't it? So if you have a prior knowledge or some basic foundation, then you can say that you will love these topics. Let me say one thing, that even though you have studied vector calculus, with regard to the UPSC exam point of view, while attending the class sessions, you feel that vector calculus is somewhat familiar to you, but you are extending your knowledge and you are going in depth of it, isn't it? As per the UPSC questions are considered. So here what is happening, you are learning for the foundations for the first time and you are solving the high level problems with regard to UPSC, because you have not studied these things at your BTech level. So you don't have any basic foundation earlier. So we need to build the foundation first, then we have to start making the pillars over it. Clear? So don't scare of it. And we have discussed the best part of it also, because many of the questions are repeated. It is purely logical. Once you present the logic clearly on paper, no marks will get deducted from you. You will get the full marks from that question. That is the advantage of abstract algebra. And the syllabus part is very limited, because if you take the calculus, you need to do a lot of problems on single model. Here, models are different and they are limited in the number. That is the advantage of abstract algebra. Fine. So, thank you very much, and we'll meet in the next session.